Good day everyone, I am Trisha Raya, and for today's video I am going to discuss and give some examples about the two topics under the hydraulics, which is the parallel pipe network and the three reservoir problems. So now, let's begin. So the first topic that we're going to discuss is the parallel pipe network. So it is said that if a main pipe is divided into two or more than two branches and joined again together downstream to form a single pipeline, such arrangement of connection of pipes will be considered as parallel. So meaning when pipes of same lengths and different diameters are connected separately in order to increase the discharge, such arrangement or connection of pipes will be considered as pipes in parallel. So to better understand, we have here an illustration. From our illustration, we can see here that we have three pipes. So we denoted the common connecting points of the three pipes as junction A and junction B. Consider this is pipe 1. So this is pipe 1, this is pipe 2, and this is pipe 3, which are connected in parallel. So for the pipe over here, we have a discharge Q. So we have a discharge Q here. This single pipe here, so once it flow and it reaches at this point, it will be split into three pipes. So it will be split into three pipes. So this single pipe will be split into three pipes. The discharge Q will separate out in Q1, in Q2, and in Q3. Here we can see that the pipes are already connected in parallel. So this is applied when we need a large amount of flow rate. So same goes here, more amount of fluid can flow from the three pipes. And eventually, so once it reach at this certain point here, so they meet each other and form as a single pipeline again. So we also have here a Q. So whatever the amount of inflow is just the same or equal to the amount of outflow. So here we can form an equation. Q is equals to Q sub 1 or the flow in pipe 1 plus Q sub 2 or the flow in pipe 2 plus the Q sub 3 or the flow in pipe 3. So in terms of head loss, so HL, in terms of HL, so HL in pipe 1 is just the same to the HL in pipe 2 and HL in pipe 3. So this is the general rule of parallel. So second equation we have here, so this is already a combination of series and parallel pipe flow. So this pipe 1 here and pipe 4, this is the series. And this pipe 2 and pipe 3, this is the parallel. So as what I've said, whatever the Q here is just the same of the Q here in pipe 4. So Q1 is just equals to Q in the pipeline 4. Then Q1 or Q4 is just the sum of the flow in pipeline 2 plus the flow in pipeline 3. So that is for the discharge. For the head loss, so HL is equals to HL in pipe 1 plus the HL in So again, the general rule of parallel, whatever the head lost here is just the same to the head lost here in pipeline 3. So 2 or 3 plus the head loss in pipeline 4. Again, head loss in pipeline 2 is just the same to the head loss in pipeline 3. So now, we already know the discharge and the head loss of the parallel pipe network. Let us proceed to the examples. And now let us begin the first example for our parallel pipe network. We have here pipeline A, B, and C are connected parallel. If the combined discharge of the three pipes equal to 0.85 cubic meter per second, and assuming they have equal values of roughness coefficient n, compute the following using the data given in the table below. So we have here pipes A, B, and C. For pipe A, the length is 500 meter and its diameter is 200 millimeter. For pipe B, we have 380 millimeters in length and 250 diameter in millimeters. So for pipeline C, we have 650 meters in length and 100 millimeter in diameter. So first, we need to determine the rate of flow in pipeline C. Next is the rate of flow in pipeline B. And lastly is the rate of flow in pipeline A in cubic meter per second. So here, I already draw the figure or the illustration. So this is pipeline A, this is pipeline B, and this is pipeline C. Then we will get the equations that we can get here. So as we can see, this is parallel pipe network. So for our head loss from the general rule, so head loss in pipeline A, B, and C are just equal. So we have here HFA is equals to HFB is equals to HFC. And we can also write it as HFB is equals to HFA, HFC is equals to HFA, since we will use these two equations here later. And for the rate of flow, we have Q is equals to Q sub A plus Q sub B plus Q sub C. Since we have a given of roughness coefficient, and we will use the Manning's formula of head loss, which is 10.29 n squared over L squared Q squared over the D or the diameter raised to 16 over 3. So first, in order for us to get the Q sub A or the rate of flow in pipeline A, so we need first to get Q sub B in terms of Q sub A and Q sub C in terms of Q sub A. So we will use these two equations here. So first, HFB is equals to HFA. Since 10.29 n squared will be cancelled, since they already have the same value, so remain is the length, the flow, and the diameter. So for pipeline B, the length is 380. So we have here 380. Then Q sub B squared all over the diameter for pipeline B is 250 millimeter, or this is equivalent to 0.25 meters raised to 16 all over 3. For pipeline A, so the length is 500 meters. So we have here 500 Q sub A. This is squared all over. The diameter for pipeline A is 200 millimeter, or this is also equivalent to 0.2 meters. So raised to 16 all over 3. Here, we will cross multiply. So, what remains here will only be q sub b squared, since we will get q sub b in terms of q sub a. So, q sub b squared is equals to, we will cross multiply, so 500 times 0.25 raised to 16 over 3, then q sub a squared all over 0.2, 16 over 3, then we have here 380. So here we will apply square root for us to cancel the squared. So squared will be cancelled. Cancel. We already have q sub b in terms of q sub a. So q sub b. So if we will input this in the calculator, we can get 2.0798 q sub a. This is the value of q sub b. So for q sub c in terms of q sub a, we will use this equation. So h of c is equals to h f a. Again, 10.29 and n squared will be cancelled. So the length in pipe C is 650. 650. Then q sub c squared all over. Its length is 100 millimeter, or this is equivalent to 0.1 meters. So raised to 16 over 3 is equals to, we will just copy this one. So 500 q sub a squared all over 0.2 raised to 16 over 3. So again, cross multiply, we will remain here is q sub c squared. Then we have here 500, then 0.1 raised to 16 over 3. (16 over 3). Then the q sub a. q sub a squared over 0.2, 16 over 3 times the 650. So again, we will apply square root to cancel the squared. So cancel, cancel. What remains in the left side is q sub c. See? So if we will input this in the calculator, we can get 1,381 q sub a. So we already got an equation of q sub c in terms of q sub a. So to get the value of q sub a, so a, for question A, so we will use this formula. So Q is just equals to Q sub A plus Q sub B plus Q sub C. So we all know that Q is equals to 0.85. So 0.85 equals to Q sub A plus the value of Q sub B here is 2.079. Q sub A plus the value of Q sub C, which is 0.1381 Q sub A. So now we can get the value of Q sub A. So shift solve in the calculator. The value of Q sub A is 0.26 cubic meter per second. So we already got the rate of flow in pipeline A. Next is to get the rate of flow in pipeline B. So Q sub B is equals to 2.079 Q sub A. Since we already have a value of Q sub A, let's just substitute. So 2.079 times 0.26. So Q sub B is equals to 0.54 cubic meter per second. And lastly, we will get the Q sub C. So for Q sub C is just equals to 0.1381 Q sub A, 0.1381 Q sub A. So let's just substitute the value of Q sub A again, which is 0.26. So Q sub C is equals to 0.036 cubic meter per second. So we already got the rate of flow of pipeline A, B, and C. And now, let's move on to the second example. So now let's move on to the second example. So given the following data for three pipes in parallel, so pipe 1, its diameter is 450 millimeter and length is 800 meter. Pipe 2, diameter is 400 millimeter and its length is 700 meter. And pipe 3 is 500 millimeter in diameter and 600 meter in length. So the total flow is 0.86 cubic meter per second. So assuming the friction factor, which is 0.02 for all pipes, evaluate the following. First, the flow in pipe 1 in cubic meter per second. Second, the flow in pipe 2 in cubic meter per second. And third is the flow in pipe 3 in cubic meter per second. So we have here the given. The total flow is 0.86 cubic meter per second and the friction factor F, which is 0.02 for all the pipes. So second thing to do is we need to get the equations that we can get here in our illustration. So we have here from the general rule of parallel pipe. So the head loss here in pipe 1 is just equal to the head loss in pipe 2 and pipe 3. Or we can also write it as HF2 is equals to HF1 or HF3 is equals to HF1 because we will use these two equations also later. So the total flow is just equals to Q sub 1 plus Q sub 2 plus Q sub 3. So since we have a friction factor given, so we will use the Darcy-Weisbach formula, which is 0.0826 FL over D5 or D raised to 5 Q squared. So first, we need to get an equation of Q sub 2 in terms of Q sub 1 and Q sub 3 in terms of Q sub 1 so that we can identify the value of Q sub 1 or the flow in pipe 1. So by that, we will use these two equations here. So HF2 is equals to HF1. So 0.F2 L2 over D2 raised to 5 Q sub 2 squared is equals to 0.0826 F1 or F sub 1 L sub 1 over D1 raised to 5, then Q sub 1 squared. So since these are just the same values, so we can cancel these two and cancel also here. What remain is we will plug the values of the length and the diameter of pipe 2 and pipe 1. So we have 700 over 0.4, 0.40 raised to 5, then Q sub 2 squared is equals to sub 2. Length in pipe 1 is 800 over 0.45 raised to 5 Q sub 1 squared. So by plugging in the calculator, we can get here 68,359.375 Q sub 2 squared equals to 43,825 Q sub 1 squared. So that Q sub 2 will remain here, we will divide this both sides by 68,359.375 and we will apply square root so that the squared will be cancelled. Here, cancel here. So what remain? So we already have a value of Q sub 2 in terms of Q sub 1. So 0.796 Q sub 1. Next, head loss in pipe 3 is equals to head loss in pipe 1. So same here, length and diameter only will be plugged in. So the length in pipe 3 is 600 all over 0.50 or 0.5 raised to 5, then q sub 3 squared is equals to 800 all over 0.45 raised to 5 q sub 1 squared. So again, by plugging in the calculator, we get 19,200 q sub 3 squared and 43,353 point 825 q sub 1 squared. Divide both sides so that q sub 3 will remain on the left side, 19,200, and apply square root to the both equation. So cancel squared. So we already have a equation of q sub 3 in terms of q sub 1, which is 1.503 q sub 1. So the first question is to get the flow in pipeline 1. So to get that, we will use this equation, q sub 1 plus q sub 2 plus q sub 3. So we all know that the total flow is 0.86. So q sub 1 plus the value of q sub 2, which is 0.796 q sub 1 plus the value of q sub 3, which is 1.503 q sub 1. So shift solve, plug in the calculator. You already have a value of flow in pipeline 1, which is 0.261 cubic meter per second. Now we can also get the flow in pipeline 2, so we will use this equation. So B q sub 2 equals to 0.796 q sub 1. So let's just substitute the value of q sub 1, so 796, then 0.261. So the answer for this is 0.208. cubic meter per second. And lastly is the flow in pipeline 3. So we will use this equation. Q3 is equals to 1.503 Q sub 1. So substitute the value of Q sub 1. We have 0.261. So our flow in pipeline 3 now is 0.392 cubic meter per second. So these are the answers. So for the last example for our parallel pipe network, so we have here a single pipeline A joins pipelines 1, 2, and 3 at junction J and merges again at junction K to form a single pipeline B, as shown in the figure. So pipelines 1, 2, and 3 are parallel to each other. The pressure heads at junctions J and K are 70 meters and 45 meters respectively. So using Hazen-Williams formula, with C1 is equals to 110 for all pipes, obtain the following. So we need first to get the flow rate in pipeline 1, second the flow rate in pipeline 2, and lastly the flow rate in pipeline 3 in cubic meter per second. So we have here the illustration. This is the pipeline 1, this is the pipeline 2, and this is the pipeline 3. So for pipeline 1, we have a diameter of 300 millimeter and its length is 3,000 meter. For pipeline 2, we have 200 millimeter diameter and 1,300 meter length. And for the third pipe, we have a 250 millimeter diameter and its length is 2,500 meter. So from the general rule of parallel pipe, so the head loss here in pipeline 1, pipeline 2, and pipeline 3 is just equal. So neglecting minor losses, the frictional loss in these pipes is equal. And neglecting the effect of kinetic energy changes, the head loss between points J and K is equal to the difference in pressure heads. So head loss is just 70 minus 45. So 70 minus 45 is 25 meters. Therefore, the value here is just 25 meters. Since we already got the value for our head loss, so we will get this in order for us to get the flow rate in the three pipes. So just substitute here for pipeline 1. So we all know that head loss is just equals to, so 25 is equals to 10.67. So for our length in pipeline 1, we have 3,000. So 3,000. So for our Q sub 1, let's just write here Q sub 1 raised to 1.85 over C, which is 110 raised to 1.85. For our diameter in pipeline 1, we have 300 millimeter, or this is equivalent to 0.3 meters. Then raised to 4.87. So our Q1, we input in the calculator, so we can get 0.0967. This is 9 cubic meter per second. So we already got the flow rate in pipeline 1. Next is the flow rate in pipeline 2. So again, head loss is just the same. So 25, then 0.67. Then the length for pipeline 2 is 1,300. Then Q sub 2 raised to 1.85 all over the C, 110. Then the diameter of pipeline 2 is 200 millimeter, or this is equivalent to 0.2 raised to 4.87. So Q sub 2, shift solve in the calculator, we can get 0.0523 cubic meter per second. So we already got the flow rate in pipeline 2. And lastly, for the flow rate in pipeline 3, HL again is just equals to 25. So 10.67 times the length of pipeline 3, which is 2,500. Then Q sub 3 raised to 1.85 all over C, which is 110 raised to 1.85. Then the diameter of pipeline pipeline 3 is 250 millimeter, or this is equals to 0.25 meters raised to 4.87. So input again in the calculator. Our discharge in pipeline, or the flow rate in pipeline 3, is 0.066 cubic meter per second. So we already got the flow rate in pipelines 1, 2, and 3. So the second topic that I'm going to discuss is all about the 3 reservoir problems. So in the 3 reservoir problems, we have case 1 and case 2. So for case 1, we have here the head loss in pipe 1 is less than the head at B. So this is the illustration. So as we can see in the illustration, we have the reservoir A, the reservoir B, and the reservoir C. So the flow of water here from reservoir A is going to be divided towards reservoir B and reservoir C. So if this happens, if the movement in the pipe 2 is towards B, therefore the piezometer reading here is higher than the elevation at B. Therefore, This is why that the head loss in pipe 1 is less than the head at B. Then we have here the head at B and the head at C. So the head at B is from the highest elevation, which is the reservoir A, up to the elevation at reservoir B. So head at C is from the highest elevation A up to the elevation at C. So this is the HC. So as for head loss, so the head loss here in pipe 1 is from the elevation at reservoir A up to the level of piezometer. So here, this is our datum here. So the head loss in pipe 2, it is just from the piezometer up to the elevation at B. And for the head loss in pipe 3, so from piezometer again up to the elevation at C. So we can derive these equations from this illustration. So again, Q1 is just the sum of Q2 plus the Q3, since the flow of water from reservoir A is going to be divided towards reservoir B and reservoir C. So HB again is just the sum of head loss in pipe 1 and the head loss in pipe 2. And HC is just the sum of head loss in pipe 1 and head loss in pipe 3. So that is for the case 1. For the case 2, we have here head loss in pipe 1 is greater than the head at B. So why? It is because due to the flow being from the highest reservoir A, so here, and from the flow on B, that is towards at junction P. So we know that when dealing to the movement of water, the movement is from the high pressure to the region of lower pressure. So as we can observe here in case 1, so the pressure is greater than the elevation. That's why the movement of water here in pipe 2 is towards B. So here in case 2, since the piezometer reading is less than the elevation at B, the movement of water here is from the reservoir B towards the junction P. So next, we also have here the HB and the HC. So our HB is from the elevation at A up to the elevation at B. So this is the HB. So for our HC, it is from the elevation at A up to the elevation at C. So as for the head loss, our head loss here is from elevation at A up to the level of the piezometer reading. So here, this line is our datum. So for the head loss at pipe 2, we have here from the elevation at B up to the piezometer. And for the elevation at pipe 3, it is from the piezometer up to the elevation at C. So as we can observe that head loss in pipe 1 is greater than the head at B. So from the illustration, we can derive these equations. So again, Q sub 1 plus Q sub 2 is just equal to Q sub 3. Then for our HB here, it is just the difference of HF1, so here, and the HF2. And for our HC here, it is just the sum of HF1 here plus the HF3. So those are the two cases of the three reservoir problems. So now let us move on to the examples. So let us now begin the first example of our three reservoir problem. So we have here three reservoirs A, B, and C are connected respectively with pipes 1, 2, and 3 joining at a common junction P. So here. And reservoir A is at elevation 80 meters. Reservoir B is at elevation 70 meters. And reservoir C is at elevation 60 meters. So the properties of each pipes are given here. So the flow from reservoir A to junction P is 0.045 cubic meter per second, and F for all pipes is 0.018. So first we need to find the elevation of the energy grade line at P in meters. Second, determine the flow on pipe 2 in cubic meter per second. And lastly is to compute the diameter appropriate for pipe 3 in millimeter. So the next thing we will do is to analyze the flow or the direction of flow here. So as we all know, by essence, so reservoir A will discharge a flow to reservoir B and reservoir C, since the elevation of reservoir A is higher than these two elevation. So reservoir B and reservoir C will receive flow from reservoir A. So next is we have here the given of the properties of each pipe. And since reservoir B will receive a flow from reservoir A, so the junction P here, or denoted as P prime, is higher than the reservoir B. So we have here, and this line here is our datum. So in order for us to get the head loss here in reservoir A, so it is from the water surface of reservoir A up to the junction P prime. And to get the head loss here in reservoir B, so it is from the junction up to the water surface of reservoir B. And for reservoir C, from the junction P prime up to the water surface of reservoir C. So given the elevations, the first thing that we need to find is the elevation of energy grade line at P. So the elevation here. In order for us to get that, so we need first to find the head loss in reservoir A, or the HF1. So 0.0826. Then F is 0.018. Then for pipe 1, we have the length of 5,000 meters. Q sub 2 is Q sub 1 is given, so 0.045 squared over the diameter of pipe 1, which is equals to 0.3. So 0.3 raised to 5. The answer for this, if we input in the calculator, is 6.195 meters. So in order for us to get this elevation here, so elevation of P prime is equals to, so elevation at A, which is 80 meters, so 80 minus the value of our HF1, so 6.195. So our elevation of P prime is 73.805 meters. So we already got the elevation of P. So next is to determine the flow on pipe 2 in cubic meter per second. So as we can see, The energy at P denoted as P prime is higher than reservoir B, thus the flow in pipe 2 is towards B. So first we need to get this head loss here. So in order for us to get that, so HF2 is equals to this just elevation of P prime minus the elevation of B, which is 70. So 73.805 minus 70. So HF2 is 3.805 meters. So now we can solve for the discharge here in pipe 2. So we will use this equation. So HF2 is equals to 3.805 equals 0.0826 times 0.018 and the length here in pipe 2 is 4,000 U sub 2 squared all over the diameter here, which is 250 millimeter or 0.25 raised to 5. So the value here, input in the calculator, shape solve, we can get value of 0.025 cubic meter per second. So we already got the flow in pipe 2 in cubic meter per second. So the last thing that we need to get is to compute the diameter appropriate for pipe 3 in millimeters, since the diameter here is not given. So at junction P here, so whatever the inflow is equals to the outflow. So as what I've said, so QA will discharge a flow to QB and Q sub C. So our equation now will be Q sub 1 is equals to Q sub 2 plus Q sub 3. Since Q sub 1 is equals to 0.045, which is already given in the problem, and Q sub 2 is equals to 0.025, we can now identify the flow in pipe 3. So the flow in pipe 3 is equals to, shape solve, 0.02 cubic meter per second. Cubic meter per second. And now, since we already have a discharge in pipe 3, we can get the here head loss in reservoir C. So HF3 is just the elevation of P prime here or in the junction minus the elevation of C. So 73.805 minus 60, our HF3 is 13.805 meters. Since we already have the value of flow in pipe 3 and the head loss in pipe 3, we can now get the diameter. So head loss in pipe 3 is 13.0, 805 is equals to 0.0826 times 0.018 times the length of pipe 3, which is 3,500, and the discharge, which is 0.02 squared, all over the diameter over diameter 53 raised to 5. So, shift solve in the calculator, we can get diameter in pipe 3, 0.172 meters. But here in the problem, so it must be in terms of millimeters. So we will convert this into millimeters. So 1 meter is equals to 1,000 millimeters. So D sub 3, or the diameter in pipe 3, is 172 millimeters. So we already got the answers for this problem. So that's all for this problem. We will proceed to the second. And now let's move on to our second example for the three reservoir problem. So we have here two reservoirs A and B, feed a third reservoir C as shown. So assuming constant reservoir water levels given, compute the following with the use of the data given in the tables below. Table. So we have here pipes 1, 2, and 3, their lengths, their diameter, and the roughness coefficient n, which is uniform to all the three pipes. So we need to determine the Q sub B being the Q sub 2, Q sub A being the Q sub 1, and Q sub C being the Q sub 3. Next is to determine the direction of flow here. So we have here reservoir A will discharge a flow, but as we can see here, the piezometer reading is lower than reservoir B. So meaning, so the movement of water will be from B up to the junction P. So we can create this first equation here, since this is Q sub 1 here, this is Q sub 2, Q sub 2, and this is Q sub 3. So from the illustration, Q sub 1 plus Q sub 2 is equivalent to Q sub 3. So this is our first equation. So in terms of head loss, so what we have here is, this is the junction P. So this line here is our datum. So from the water surface of reservoir A up to the junction P, this is our head loss 1, or the head loss in reservoir A. So for the head loss in reservoir B, so denoted as HF2, it is from the water surface of reservoir B up to the junction P. And for the head loss in reservoir C, or denoted as HF3, so it is from the junction up to the water surface of reservoir C. So HB here and HC, so we can get the head of reservoir B by subtracting the elevation A to the elevations B. So we have here 80 minus 70. This is the head of reservoir B, which is 10 meters. So for the head of reservoir C, so 80 minus 60, then we can get 20 meters. It is the head of the reservoir C. So HB here is just the sum of head loss here. I mean the difference of HF1 minus the HF2. So that is the HB, which is 10 meters. So for our HC, so it is just the sum of HF1 and HF3. So we got 20 meters. So HF2 also plus HF3 is equals to 10 meters. Since we have a given of roughness coefficient n, we will use the Manning's formula. Since we have the values of HB here and HC, as we can see in these the relationships of these formulas, so we can solve for the value for HF. So meaning we are going to get HF2 in terms of HF1 and HF3 in terms of HF1. And then after use the first equation so that we can get the value of HF1. So let's do that by getting the Q equation. So Q here is equals to HF d 16 over 3 all over 10.29 and squared L. So square root. So let's use this Q formula, then substitute the value of HF based on this. So we need first to get the HF. So HF2 is equals to HF1 minus 10. So 10. Then HF3, 20 minus the HF1. So after that, we will use this first equation. So at 1, so Q1 plus Q2 is equals to Q3. Then we will use this formula. So HF1, then 0.4, which is the diameter in pipe 1, then raised to 16 all over 3, over, since 10.29 and n squared is just the same in all three pipes, so it will be cancelled. The remain here is the length. So the length in pipe 1 is 1,800. Then square root plus HF1 minus 10, this is from here. Then the diameter of pipe 2 is 0.5 raised to 16 all over 3 over the 2000, which is the length of pipe 2. Then square root equals 20 minus HF1. This is from this equation. So times the diameter of pipe 3 raised to 16 over 3 over the length of pipe 3, which is 4,000, then square root. So now we can identify the value of HF1. So if we will input that in our calculator, then shift solve, we can get 16.2 meters. So we already have this. And by substitution, so substitute the value of HF1 here. So HF2 will be HF1, which is 16.2 minus 10, which is equals to 6.2 meters. And then for our HF3, 20 minus HF1, which is 16.2, we have 3.8 meters. Since we already got the value of these three head loss, then we can get their flow. So for the first question is we need to get the flow in pipe 2. So HF2 is 6.2, then 10.29. This is for the pipe 2. Then 0.011 squared. Then the 2000, which is the length, Q sub 2 squared all over the diameter, which is 0.5 raised to 16 over 3. So Q sub 2 now is equals to 0.249 meters, which is also the Q sub B. So we already have the value for this. So next is to identify the flow in pipe 1. So HF1 is just 16.2. So 16.2, 10.29 again, times 0.011 squared. Then 1800 for the length, Q sub 1 squared all over its diameter, which is 0.4. 16 all over 3. So shift solve, Q sub 1 is equals to 0.234 cubic meter per second. Or this is the Q sub A. And for the last question is to get the Q sub 3. So HF3 is equals to 3.8. So 10.29, 0.011 squared. Its length is 4,000. Then Q sub 3 squared all over its diameter, which is 0.816 over 3. So shift solve again. The value for our Q sub 3 is equals to 0.482 cubic meters per second, or this is our Q sub C. So we already got the answers. Now, let's move on to the last example. So for the last example of 3 reservoir problems, so in the figure below, valve F is partly closed, so creating a head loss of 1.093 meters. So here. Then when the flow through the valve is 0.0283 cubic meter per second, so use Hazen-Williams formula. So A, what is the head loss of pipeline 3? B, what is the discharge of pipeline 1? And C, what is the length of line 1? So first, in order for us to get the head loss at pipe 3, so we need first to get the head loss of this pipe 2. So to get the head loss of pipe 2, so HF then 0.64 L. So our length here is 300. Then for the flow in this valve, so we have a given 0.0283 raised to 1.85 over C, which is 80 here. So 80, then raised to 1.85, then 0.3 diameter raised to 4.87. So we have a value of 0.463. So 463 meters. So to get the HF2, we just add 1.093 here and this one plus 0.463. We already have a value of our head loss at 2, which is 1.556. And we can now get the head loss at 53, which is here 6.10 minus the HF2. So 6.10 minus HF2, which is 1.556. So HF3 is equals to 4.544 meters. So that is for the first unknown. So second question is, what is the discharge of pipeline 1? So for the discharge, we will use this equation. So Q sub 1 plus Q sub 2 is equals to Q sub 3. So first, we need, in order for us to get the Q sub 3, so we will use the loss equation in pipe 3. So 10.64. So the length in pipe 3 is 1,525 times Q sub 3 raised to 1.85 all over 120, which is the C, raised to 1.85, and 0.3 diameter raised to 4.87. We already have. So since our HF3 is equals to 4.544, so let's just substitute 4.5544. So input in the calculator, then shift solve. Our Q sub 3 is 0.061 cubic meter per second. So we can already get the q sub 1 since we already have a value of q sub 2. So q sub 1 plus q sub 2 is equals to q sub 3. So q sub 1 plus q sub 2 is 0.0283, which is already given. Is equals to q sub 3, which is 0.061. Should solve, our q sub 1 is equals to 0.0327 cubic meter per second. So we have already the value of flow in pipe 1. So for the last question, what is the length of line 1? So to get that, we need to get first this had loss in pipe 1. So HF1 is just equals to this HF2 minus this HF2 minus the 0.61. So we already know that HF2 is here. HF2 is 1.556. So 1.556 minus 0.61. So our HF1 is just equals to 0.946 meters. Since we already have the value of HF1, we can now get the length. So HF1, which is 0.946, is equals to 10.64 times the L. Then 0.0327 raised to 1.85 over 100. So 100. Then raised to 1.85. Then the diameter, which is 0.25, raised to 4.87. So shift solve, input in the calculator, we can get 291.75 meters. So that's all. These are the answers.